Hi, in this video we will orthogonally diagonalize a symmetric matrix. In other words, for a symmetric matrix A, we will find an orthogonal matrix Q and a diagonal matrix D such that Q transpose AQ is equal to D. Well, the steps to do this starts with finding eigenvalues of A. It means that first find the characteristic polynomial, solve it, and find eigenvalues. Well, here it has two eigenvalues, -1 and 5. Then step 2 is find the basis for the eigenspaces of each one of these eigenvalues. So find a basis for each eigenspace. So we have E of a -1 and E of 5. Well, if you solve the A minus lambda x equal to 0, you notice that E -1 is the span of two vectors, which are -1, 1, 0 and -1, 0, 1. And eigenspace of lambda equal to 5 has only is the span of one vector, 1, 1, 1. From here, well, you can see that B of let me call it -1. So we can form a basis for E -1. Just take these elements. These are independent vectors and they span the whole E -1, so it is a basis for E -1. From this one, B of 5 form a basis, while 1, 1, 1 is a basis for E5. Okay, well, this is not complete yet. We have to do a little bit more work. If we were looking just for an invertible matrix, we can took these elements of these vectors of these bases and put them in the column and form that invertible matrix. But now we are looking for orthogonal matrix. That means that we have to construct an orthonormal basis for each E lambda. So I have B -1, which is this. I have to make this one into construct an orthonormal basis from this one. So for that, remember, we need to do Gram-Schmidt first. So from here, so if this is x1, this is x2, v1 is going to be x1, which is -1, 1, 0, and v2 is going to be x2 minus projection of x2 on v1 here. So you get -1, 0, 1 minus projection on v1, and there's a scalar multiple that is x2 times v dot v1. So here, there you get 1 plus 0 plus 0, and in the denominator you have a negative 1 squared plus 1 squared plus 0 squared. So this way we have negative 1 plus 1 over 2. This will be negative 1 over 2. This is 0 minus 1 over 2, and this is just 1. So from this, we constructed this orthogonal basis, which is negative 1, 1, 0, and negative half, 1. Then we have to normalize these guys. So normalization here is that divide each one or multiply each one by 1 over length of each. So this one has length root 2, so this will be negative 1 over root 2, 1 over root 2, and 0. How about length of this one? So it is half squared plus half squared plus 1, and that way 1 squared. That way we have 4, 1 plus 1 plus 4, which is 6 over 4. Yes, and that is just 3 over 2 root. Yes, and well, if we do that, what we get, maybe it would be better to write this one as root 6 over 2. Now 1 over that will cancel that. This will be 1 over root 6, 1 over root 6, and that last one is going to be 2 over root 6. Okay, so this is the orthonormal basis for E eigenspace of negative 1. Okay, how about eigenspace of 5? So for basis that we have there is 1, 1, 1. So do we need to do a first Gram-Schmidt? Well, you can always do, but if you have only one vector in your basis, Gram-Schmidt wouldn't do anything to that matrix, just because the first vector is equal to the original first vector in the Gram-Schmidt process. But in the normalization, you have to multiply the vector by 1 over its length. Length of this vector is root 3, so we'll have 1 over root 3, 1 over root 3, 1 over root 3. So we have now, obviously, okay, let me write this one also. This is orthonormal basis for E5. Now that we have everything, D is going to be lambda is equal to negative 1, but we had 2 of those. The multiplicity of negative 1 was 2 and 5 was 1. So that's D. How about Q? Put the elements in the orthonormal basis for each eigenvector corresponding to their eigenvalue. So for negative 1, I have 2 of those, so negative 1 over root 5. Sorry, negative 1 over root 2, 1 over root 2, 0. The other one is negative 1 over root 6, negative 1 over root 6, and 2 over root 6. And for the lambda equal to 5, we have only one element in the orthonormal basis, and that is this guy. Well, if you choose that, Q transpose A, Q is going to be equal to D. It's an interesting exercise just to check that you can multiply and get that done. Okay.